Hi folks, welcome to the extension video for 6.2. So in class we talked a little bit about how sine and cosecant are reciprocal functions, and we use that definition of reciprocal to help us generate the graph of cosecant. And so it was a good chance for us to review the graph of sine, which you need to know for exam 2, the domain, the range, whether it's odd or even or neither. But it was also a cool chance to take a look at why the cosecant graph looks the way it looks. And so one thing that we noticed is that every time we divided by a 0 in sine to get cosecant, we actually ended up with a vertical asymptote, okay? And so that's something we're just gonna write down right here before we move on to the other ones, that one of the patterns that's sort of interesting is that the vertical asymptotes of cosecant come from the zeros of sine. Okay, so the zeros of sine, meaning all the x-intercepts of sine, will give us vertical asymptotes in cosecant. Okay. All right, so knowing that, let's take a look at cosine and use that to generate secant, or its reciprocal function, okay? So we know that secant of theta equals 1 over cosine theta, and that comes from our reciprocal function, okay? And we also know that the graph of cosine looks like this. We talked about how the domain is from negative infinity to infinity, or we could call it all real numbers. We said that the range of cosine was from -1, and so that bracket means including -1, all the way to 1. We can close it with a bracket because we also include 1. And if we look for symmetry here, we can see that cosine is an even function because it's symmetric about the y-axis. And one thing to keep in mind is we can also say that as f of x equals f of negative x, okay? And so let's use the same reasoning we did with cosine to think about how we get the graph of secant, okay? So this graph of secant is right here. And this is the picture that you get when you go on Desmos and you graph secant, right? But let's kind of explore where it came from. So it turns out that that pattern we established earlier with sine and cosecant also holds true for cosine and secant, meaning the vertical asymptotes of secant come from the x-intercepts of cosine, okay? And so let's use that lime green color again to kind of see. All right, so I see that there is an x-intercept at pi over 2, and one at 3 pi over 2, and negative pi over 2, and negative 3 pi over 2. And if we look on this graph, let me sort of zoom in a little bit so we can see both graphs at the same time. We can see that this has a vertical asymptote at the same angle that cosine has a 0. And that happens again at pi over 2. It happens again at negative pi over 2. Happens again at negative 3 pi over 2. Okay? So all of those x-intercepts turn into vertical asymptotes for secant. Now, if we use that same idea of taking the reciprocal of a number, this point up here, the orange one, has a value of 1, and the reciprocal of 1 is 1. So this point on secant should also be 1. And the same thing holds true for the negative ones. Those reciprocals are -1, so we get those points, okay? And if we picked some other ones like 1/2, we would get a value of 2 here, all right? Kind of like we did with the cosecant graph. Now let's take a look at the domain and the range, all right? And if we look at the domain, we can see that it's going to be all real numbers except for all the vertical asymptotes. Okay, so this part is going to describe the vertical asymptotes, right? So it's easier to say everything except for these few points that follow a pattern. It's easier to say that than it is to say this piece and this piece and this piece and this piece and try and list out all the pieces, okay? So let's see. This time, I want to say that it can't be pi over 2, okay? And then every multiple, that's what that K stands for, the multiple of pi. Because if we take pi over 2 and we add pi, we'll get 3 pi over 2, right? So that would be pi over 2, add pi, I get 3 pi over 2. Well, what if I take pi over 2 and I subtract pi? Negative pi over 2. If I subtract another one, negative 3 pi over 2. Okay, so this formula here just kind of describes those multiples. Instead of writing multiples of pi out in words, we say k pi. Now, if you want to be extra fancy, k has to be an integer. So to say that, we say k, this little e, and a fancy z. Okay, so this is k is an integer. All right. Again, you don't need to know this for the test, but I think it's nice to be able to read your way through some things and help they make a little bit more sense, okay? Now for our range, well, it looks like we have sort of all those bottom curves that go up to -1. So we could say from -infinity to -1, and we include that, and 1 to infinity. Okay, so we're missing all the y values between -1 and 1, but we have everything else, all those parabola looking things that we have, okay? Now, if we want to choose even, odd, or neither, we could use some reasoning we had in class, which is that if cosine is even, so is secant, okay? So since cosine is even, so is secant, all right? But we could also look at the symmetry here, and we see that it is symmetric about the y-axis, okay? Meaning if I fold the graph over the y-axis, the two halves will match, right? And a third way I can say even is that f of x equals f of negative x, right? So all three of those are ways we can show that secant is even. All right, so let's take a look at one more pair of graphs. So we have tangent and cotangent. Now, our tangent graph, as someone very astutely pointed out in class, comes from our division of sine and cosine. And that's where those vertical asymptotes come from, okay? So after I finish drawing this last vertical asymptote, let's go ahead and write out that the vertical asymptotes of tangent come from the x-intercepts of cosine, right? Because tangent is sine divided by cosine. So everywhere that cosine is 0, so is tangent. And that's where we say our domain is all real numbers, except x cannot be pi over 2 or any multiple of pi plus that pi over 2. And again, if you want to be fancy, you could say k is an integer, That's what that part says, okay? Now our range, we said for tangent, was from negative infinity to positive infinity, or we could say all real numbers, okay? So those two are interchangeable. And we already know from the earlier work we did that tangent is odd. And we can say that because f of negative x equals negative f of x. We can also say that it is symmetric about the origin, okay? And those are two different ways of saying, hey, this function is definitely odd. All right, so let's use this graph to think about how we might be able to come up with the graph of cotangent, okay? So if we think about the relationship between tangent and cotangent, we know that cotangent is 1 over tangent. That's one way to think about it, okay? So what that means is cotangent has vertical asymptotes when tangent x is 0, okay? So let's see if that's true and find all those zeros. So here, tangent is 0. Oops, let's put those on the same page so we can see that a little bit better. So that blue dot is where tangent is 0. Well, if we look at the graph of cotangent, sure looks like there's a vertical asymptote there, okay? And let's check out the other ones. 0, vertical asymptote. 0, vertical asymptote, okay? And we could take all these zeros of tangent will be the vertical asymptotes of cotangent, all right? And if we took all of the coordinates from tangent and we found their reciprocals, we would get a graph that looks like cotangent, okay? All right, so let's take a look at the domain for cotangent. Well, it looks like it could be all real numbers, except x cannot equal any of those vertical asymptotes. And when I look at all the vertical asymptotes, they look like they're multiples of pi, right? We have pi, negative pi, 2 pi, negative 2 pi. And so we could say all real numbers except x cannot equal a multiple of pi, where k is an integer, okay? And if we think about the range, well, these curves go all the way up and all the way down. There's no sort of pieces that are missing along the y values, right? If I pick this middle one and kind of trace it, it goes all the way from top to bottom without skipping anything. So we can say from negative infinity to infinity, or all real numbers, okay? And now our last piece here, determining whether this is even, odd, or neither. Well, I don't think it's even, because when I sort of reflect them over the center, the y-axis, those pieces are not the same, okay? And we might even know that if tangent is odd, so is cotangent, right? But we could also look at the graph and say it's symmetric about the origin. And then the last way we could say it's odd, which will be important for exam 2, is that f of negative x equals negative f of x, okay? And so let me zoom out so you can see the graphs of tangent and cotangent on the same page. But basically, I want us to think about like the reasoning why these graphs look the way they look, but I don't really need us to know exactly how they look, okay? So I hope this was helpful, and I will see you in class on Wednesday.